Okay, so in this video, we're going to be looking at an example of an undamped spring mass system. I've written the equation, the formula, if you will, up here for a spring mass system, a mechanical, the equation for mechanical vibrations. This version includes damping, right? This term here is the one that tells us about how much damping there is in the system. And this term here, the right-hand side, tells us about any external forces. In this video in particular, we're going to be looking at a form of this equation that excludes the damping, hence undamped, so we get just this left-hand side, and excludes any external forces. So we have a homogeneous, undamped equation. Now, before we get into any of that even, I'm going to take a minute and do some trigonometry review. I'm going to do that here, and then ultimately I will probably erase it as I'll need the room. But I want to make a note of this formula or this trigonometric identity. I'm going to take r times the cosine of omega t minus delta. There's a reason I've chosen these parameters to work with, because once we do the work over here, these are the parameters we're going to be using, and I want them to be familiar when we get there. But in this form, this expression should be familiar from trigonometry, and we have an identity that lets us rewrite that as r times the cosine of the difference of two angles is the cosine of the first angle times the cosine of the second angle. And if this is a minus, then this is going to be a plus. And I'll get plus the sine of the first angle. Let me see if I can move this over. Oh, I'll have to do it in parts, but yes, I can. Okay. The sine of the first angle times the sine of the second angle. So I get sine delta there. I'll close the parentheses. Now I'm going to distribute those r, and I'm going to also change the order. Instead of, because multiplication is commutative, I can write cosine omega t times cosine delta, or I can choose to write cosine delta cosine omega t plus r sine delta times sine omega t. And I want us to have this in our heads, that I can choose to write this expression either this way or the other way. Now, at some point I may have to erase this, and if I do, I'll write it somewhere else as a summary. Let's see if I can get away with not erasing it first. Okay, so solutions to this thing are going to look like e to the power of rt, and the r comes from the characteristic equation. Here I'm going to have mr squared plus k equals 0. Subtract k from both sides, you get mr squared equals negative k. Divide by m, we get r squared equals negative k over m. And so r is going to be I times the square root of k over m. By way of reminder, k is just this thing we call the spring constant. It's the constant of proportionality. If I know how much force it takes to extend a spring to a certain length beyond its natural length, then I can determine that k value. That's called the spring constant, or the constant of proportionality. And m, I've made a very messy m here, haven't I? M is the mass of the thing, if there is one, attached to the end of the spring. So we have this value here, this square root of k over m. That's just going to be some constant for any given system, right? We will know what the mass of any object attached to the end of the spring is. We will know, or we will be able to determine what the spring constant is. So once we know what those are, they're constant. We take the square root of the ratio, and we have some other constant. And in a lot of cases, including the case of your textbook, we can say that the square root of k over m, we'll just call that something else. And your textbook calls it omega sub 0, omega naught. And this is also known as the natural frequency of the system. And we'll talk in a few minutes, we'll talk about what that means. But the naught, the sub-zero, the subscript 0 here refers to the fact that this is this omega, this frequency, is the natural frequency. It's the frequency that occurs when the system is at rest. So this constant here, this spring constant, and this mass are constants whose ratio and square root can be represented by some other thing. It's a little easier to write. And we use the subscript 0 to indicate the natural frequency rather than some other frequency that might be occurring either in or to the system. And this is why I chose to use omega over here. This omega, I could replace that with omega naught. And it means exactly the same thing. All the algebra, all the trigonometry, all the identity work still applies. Okay, I've just called it omega naught instead of omega. Okay, so now also recall that, let's see, where did we do that? Complex roots of the characteristic equation. That was section 3.3, and the title of that section was Complex Roots of the Characteristic Equation. So if this piece doesn't make sense, I would encourage you to go back and take a look at that. Once I know that what my r's look like in this case, I'm basically going to have a u sub 1 that looks like e to the power of I, remember this is I omega naught times t, and I'm going to have a u sub 2 that's e to the negative I omega naught t. But that can also be written as cosine omega naught t plus I sine omega naught t, or cosine of omega naught t minus I sine omega naught t. And the good news is we only need one of these, so we're just going to choose one to work with. I'll use u1. I want to erase the other one, but perhaps I'll cross it out just so that we remember where we were going with this. And then even better news is that if from, let's see, what number theorem was that? 3.2.6. It didn't have a name, I don't think. I don't recall offhand. But the theorem essentially says, there's two theorems I'm going to work with here. One of them says that if you have a solution y equals a plus bi, that is a solution to a second order differential equation, then y equals a and y equals b without the I are also solutions to that system. So I'm going to use that to say that y or u sub h, that's my solution to a homogeneous system, a homogeneous equation, right? Actually, it's this one up here. Sorry, I was pointing at the wrong one there. U sub h is a, which is in this case the cosine of omega t times some constant plus the other solution, which is sine of omega t times some other constant. All right, now here's where the magic happens. Remember this work that we did over here on the right-hand side? Let me erase this. Let me highlight some things here. I'll start by highlighting this r cosine delta, and I will also highlight r sine delta. And then I will point out that in the equation that I have down here, this C1 matches that r cosine delta, and the C2 matches the r sine delta. So we're effectively saying here that if delta is some angle, then delta is a constant. The cosine of delta is a constant. R is just a constant, right? So this whole thing here is just a constant. And down here, I've called it C1. This is just a constant, and here I've called it C2. So that means that I can write U sub h as r cosine of omega naught t minus delta. So I don't know what r is, but whatever it is, it's constant. So I can write this in this form, or I can write it in this form. I have it in the first form. I have it in this form here. And I'm just choosing to write it in a different form. So I have r cosine delta equals C1. That just means that whatever this constant is, I'm choosing to think of it this way. And C1 is composed of both r and cosine of delta. And when I choose to write this expression in this form, what I'm saying is that this thing here is just a single cosine function whose graph has been shifted over by some value delta, right? It's just been horizontally shifted. When I look at this expression here, what I see is an amplitude, and I see a frequency, and I see a phase shift. So hopefully from trigonometry, you will remember what all of those things are. Maybe you'll even remember that we often write those equations in the form r times the cosine of, we'll factor that out, and then we'll write t minus, right, since we factored that out. And that tells us exactly what our horizontal shift is, right? This is some horizontal shift, but it's actually magnified at the moment. When I factor that constant out there, I get this horizontal shift. So now I can look at a graph of this thing, and I can tell you what its amplitude is. I can tell you what its frequency is, and I can tell you what its shift is. In this form, I couldn't necessarily tell you that. Another thing that's really cool about this is that I could think of C1 as r cosine delta and C2 as r sine delta, so that delta is some angle in a right triangle. And let me see, I'll do a little bit more algebra over here. I've got the cosine of delta is equal to the c, this implies, it's not equal to, C1 over r, and this implies that the sine of delta is C2 over r. And so that makes r my hypotenuse, C2 my opposite, and C1 my adjacent. So it all comes together, it all ties together. This also tells us that I can write r as the square root of C1 squared plus C2 squared. And I can think of delta as the arctangent of C2 over C1. Also remember from trigonometry, see, I'll move a few things around here. It's very strange what my software decides is going to be connected. I've never really been able to figure that out. Also recall that this number here tells us something about the frequency of a cosine graph. A cosine graph with a frequency of 1 might look like that. Of course, it continues forever. With a higher frequency, it might look like that. And with a lower frequency, it might look like that, right? When we say that the period of a graph is the amount of time, or the amount of distance, if t is the independent variable axis, that it takes to complete one cycle. So the period of this graph is much bigger than the period of the white graph, and that's bigger than the period of the pink graph. And how would you figure that out? Well, a normal cosine graph completes one cycle in 2 pi. So to figure out its period, we take 2 pi and divide it up into however many cycles there are in that amount of space, and that's what we call our period. And we can put that back into terms of, again, let me see if I can move this around a little bit. Do it that way. We can put that back into terms, being in terms of k and w. If I write that as 2 pi over, remember that omega naught, I said k and w, didn't I? K and m. omega w, omega naught, we said, was the square root of k over m. So let's write that as 2 pi over k over m to the 1/2 power, and that becomes 2 pi times m over k to the 1/2 power. All right, let's see if I've covered everything here. I'm going to rewrite this period out here. Period is equal to 2 pi times m over k to the power of 1/2, or the square root of 1 over k, of m over k. That's my period. That's the period of the function, period of the graph. We have discussed natural frequency, which is, we say is omega naught, but that stands for something else as well. I did not write this down anywhere, so I'll do that now. R is the amplitude, and delta is what we call the phase. Now, I think that's a little bit misleading because I think of a phase shift as being how far you have to move a graph to the left or right, right? And that's indicated in part by delta, but the actual shift, remember, has to be computed this way. But we do call delta the phase, or sometimes the phase angle. And the equation that we came up with, now that we know what all the parts of it mean and what they represent and what they do, we can say that, well, we can give this thing a name too. Although more than a name, we're going to talk about what it describes. It describes something called simple harmonic motion. Also sometimes called periodic motion. So if you graph this thing, let's say you let r be some constant 2 or 5 or the square root of 13, give omega a constant value and delta a constant value, then you'll be able to plug this into a graphing calculator or Desmos or something, you'll get a graph. And the graph that you get will have a constant amplitude. And the reason for that is that there's nothing to stop whatever spring is bouncing on, or whatever weight is bouncing up and down on a spring. There's nothing to stop it from bouncing. There's no damping, right? So we're going to talk in a future video about a system like this where there is damping. But for right now, when you graph this thing, you would have something that looked like this. It will not diminish like this, right? This would be a damped system. This is an undamped system. So that R is having a constant effect on the graph of this shifted cosine function. Okay, let's take a look at an example, but I'll do that on another slide. All right, I think I'll start by just reading through this example so that we have laid the groundwork for what we're going to be looking for. An object attached to a spring undergoes simple harmonic motion modeled by mass times the second derivative of x with respect to t plus k times x equals 0. A mass of 15 kilograms is known to stretch the string by 0.25 meters. A mass of 2 kilograms is attached and displaced 0.55 meters above equilibrium and then set in motion with an initial velocity of 1.5 meters per second. Use this information to find the equation of motion. All right, there are a couple of things to observe here. One is that it's not clear from the way this particular problem is written that this mass of 2 kilograms is attached after this 15 kilograms has been removed. This 15 kilograms is just being used to give you a piece of known information. We know that if we attached 15 kilograms, the string would stretch by this much. We can use this sentence to find the spring constant, k. And that's actually the first thing we need to do in this problem. So we'll do that first in just a minute. Something else to notice, though, is that the equation, the differential equation, is given in a form that's a little different from the ones that we've been working with up to now in this video sequence. What's good about the form that it's given in, let me back up. I could rewrite this as m, I guess I'll go with x double prime plus kx equals 0, and they could have given it to us in that form. That's probably how I'll work with it. But this piece right here tells me what the independent and dependent variables are. In other words, this function is a function of x in terms of t. And if I were to write it out, I would say x of t equals, so that's what I'm going to be looking for, right? The solutions to this thing are x's, but not in the same way as they would be solutions to, say, a quadratic equation like x squared plus 6x plus 9 or something like that. They are the answers, they're the dependent variable, and the independent variable in this case is t. So rewriting this as x double prime is definitely going to be easier to work with, but it doesn't tell me what the independent variable is. That's okay. I have that now. I have that information. So in the context of this problem, this notation is fine as long as I keep that in mind. So our first task here is to figure out what k is. And remember that we have an equation f sub x equals negative KL, that's called Hooke's law, that tells us if we know the length by which a spring has been elongated and the force required to elongate it by that amount, then we can figure out what K is. And we have that information in this problem. We don't have it in quite the right form. We don't know what Fs is. We don't know what the spring force is, but we can find out. Remember that the weight plus the spring force is equal to 0, because the weight of an object pulling down on a spring or down on a system is being counteracted by the force of the spring pulling it back up again. So the combination of these things, the sum of these things is 0. That means that we can write the spring force as negative W. And since W is equal to mass times acceleration due to gravity, we can write this little equation. And that gives us mass, which was 15, times acceleration due to gravity. Now we're in metric here, so we're going to use 9.81 meters per second squared. You may have learned 9.8, that's fine. In the problem that I'm modeling here, the instructions actually told me to use this constant as an approximation for acceleration due to gravity. So I'm using that specifically because I was told to use that level of accuracy. If I work this out on my calculator, I get approximately negative 147.15. So now I have a value that I can replace f sub s with. Let's do that. I'm going to write negative 147.15, and then I'm going to check back to the calculator and see how accurate was that as I mentally rounded off. Did I round off too far? And in fact, that's the entire value that I have. That doesn't mean it's the accurate value. It doesn't mean it's accurate to the level I was asked to use. But I have written down the entire decimal here. There are no numbers that I left off. I haven't rounded what the calculator display gave me, but I do have to keep in mind that this is an approximation as well. Okay, so there's my f sub s, and I'm going to say that that's equal to negative k times L. Well, what is L? L, we were told, not directly, but we were told that if we applied 15 kilometers, if we applied 15 kilograms, we would add to the length of the spring by 0.25 meters. So that's going to be times 0.25. And then, of course, I'll divide both sides by negative 0.25. And that will give me k equals 588.6. Now, once I have this value, it's fixed for this situation, right? I now know what k is. I know what goes in that spot. No matter what my masses are, no matter what my displacements are, k is set. It's 588.6. So I'm going to rewrite this differential equation. I'll use that shorthand, just x double prime instead, but I'm going to replace k with 588.6. And I think I'll do that. Where should I do that? Good question. Can I move this stuff over? Only piecemeal. It's just bizarre. I have no idea how it makes that decision. Okay, so let's rewrite the equation. M times the second derivative of x with respect to t plus k, which we now know to be 588.6 times x equals 0. So we started with this very generic differential equation, and we've used some information to fine-tune it a little bit. But what we're going to do now is fine-tune it even further. So assume that I've grabbed this spring not from some already set up system, but out of a bin somewhere. And on the bin, it's labeled that this particular spring has the property that once upon a time somebody tested it at a mass of 15 kilograms, lengthened the string or elongated the string by 0.25 meters. So we used that information to find K, but now we know what K is for this particular string. K is this number here. Now we're told to go set it up on the table and attach a 2 kilogram mass. I was just about to say a 2 kilogram weight there, but it is not a weight, it is a mass. Weight is mass times acceleration due to gravity. All we know is that this is the mass of the thing. So I'm going to replace mass with 2 in my equation. And now I have a differential equation that I can solve. If I have enough other information to do that. And I do, although it's still going to take some effort to figure things out. Notice that when I displace this thing by 0.55 meters, I'm doing it at the beginning of whatever experiment I might be conducting, right? So I'm saying attach the spring, maybe let it come to rest, and then it's not really super clear from the wording here, but this is often what you're dealing with. Let it come to rest and then displace it. In other words, push it above equilibrium. So push it up slightly, half a meter, a little more than half a meter, before you let it go. All right, so what that tells us is that at time 0, I'm using u when I should be using x. X of 0 equals 0.55, right? So I've displaced this thing once it's attached and I'm getting ready to set it in motion. Before I set it in motion, I displace it 0.55 meters. So that's telling me that the initial condition of position is that at time 0, the displacement is 0.55 meters. Now, something else we have to be very careful with here is that our displacement, when you take a spring with no mass on it and you attach a spring to it, that spring has a positive effect. And so we say that downward in this instance, in this setup, is the positive direction. So if I'm displacing my mass to 0.55 meters above equilibrium, I'm going to have to push it up, which means that my displacement at time 0 is actually negative. Okay, now the other piece of information we're told here is that it's set in motion before we don't just let it go. We let it go with a little bit of a push. And that push, that initial velocity is 1.5 meters per second. So now we also know that the velocity of the thing at time 0 is given as a constant. So we have these initial conditions. And with that, we can figure out what the solution to this equation is. Given my propensity for running out of room and how little room I have to start with here, I'm going to erase this column and this column. We've used this information to figure out what our spring constant was and what our K value was. And we've actually used that now. So I'm going to go ahead and erase those, and then I'll continue from there. Okay, so now I have a second order homogeneous differential equation, and I know how to solve those. So let's go ahead and use this as practice. Recall that solutions to this will look like x sub n equals for the nth solution. Well, we're only going to have two, but I don't want to say x sub 1 or x sub 2. I'm going to say x sub n. It's going to look like e to the power of rt, where r comes from the corresponding, the word has just evaded me, characteristic equation that looks like that. Now, it's tempting to say, oh, there's an x there, so there should be an r there. But remember that this is the second derivative of x translates to the second power of r. The first derivative of x, there isn't one, translates to the first power of r. And the 0th derivative of x, that's the function with no derivatives taken, translates to the 0th power of r. So this is r to the power of 0, which is 1. So there is no r in this term here. We go to solve this, and we end up with, let's see, we could divide both sides by 2 first. Let's go ahead and do that. We could subtract the 580 for both sides first and then divide by 2. It doesn't really matter. So actually, let's do that. Let's go 2r squared equals negative 588.6. So r squared equals negative 294.3. And so r then must be equal to plus or minus I times the square root of 294.3. Okay, so my solutions should look something like this. X sub 1 and x sub 2 are e to the power of I times the root of 294.3 times t, and e equals negative I times the square root of 294.3 times t. Remember, though, that those can also be written as, I'll just do x sub 1 here, the cosine of the square root of 294.3 times t plus I times the sine of the square root of 294.3 times t. So this solution here, let me highlight them. This solution here to the homogeneous differential equation translates to, corresponds to, is equivalent to this solution. They're the same thing in a completely different form. Remember also that for our purposes with complex solutions to the characteristic equation, we actually only need one. So I'm not going to bother with x sub 2, just going to use x sub 1. But also remember that that theorem, oh gosh, 2.3.6, I want to say. Let's see if I have it written down here. Yeah, 3.2.6 tells me that if this statement is true, a solution looks like that, where this is a real part and this is an imaginary part. If that's true, then I have, let's call them x3 and x4. Two solutions are the real part and separately the imaginary part's real component. In other words, you just drop the I. If you don't remember this piece, go back and look at section 3.2, because that's where we talked about how we get away with doing this. Now, if I have two solutions to a second order homogeneous differential equation, then I can write the homogeneous solution, the general solution to the homogeneous equation as cosine, oops, I forgot my square root, 294.3 t plus, I think you'll notice I'm leaving some room here, 294.3 t as a linear combination of those, right? Some constant times the first solution plus a different, potentially different constant times the other solution. So now we have a solution, and we don't know the constants here yet, but we have a general solution to the homogeneous case, the homogeneous case. But the whole problem is the homogeneous case, right? So I don't need, in this case, to find a y sub p or an x sub p that would be. I don't need that because I would only need that if this were a non-homogeneous problem, and it's not, it's homogeneous. So I have my general solution. The question now is what's the actual solution? Because I have these initial conditions here, I can plug them in to find out what C1 and C2 are. So let's do that. I'm going to try to squeeze it in underneath here. I have the original equation, the original answer, if you will, the original x value is negative 0, wrong pen color there, negative 0.55 when the input t is 0. So that's going to give me C1 times the cosine of 0 plus C2 times the sine of 0. And of course, this goes to 0 because the sine of 0 is 0. And the cosine of 0 is 1, so this becomes 1. And I end up with the equation negative 0.55 equals C1. So now I know what my C1 value is. Well, that was easy. Let's go ahead and highlight that. And so now I need to figure out what C2 is. I have C1, I need C2. But the only other initial condition I have is a value for when the derivative is evaluated at 0. So if this thing here is my solution, then I need its derivative. Actually, that's not the one I want to use, is it? No, I want to use x sub h. Maybe I should highlight that as well. I'll highlight that one in 0, in yellow. That's 0 on the brain. Okay, so if I take that and I find its derivative, then I'll have somewhere to plug this other set of conditions in. So let's do that. I'm going to try to squeeze that in up here. I have a product, but it's the product of a constant and a function. So it's just going to be this constant times the derivative of this, plus this constant times the derivative of this, which will be, I was going to do this part later, but this square, the square root of 294.3 is approximately 17.2. So I'm going to use that instead of that square root because otherwise I'm going to run out of room. So I have h sub x's prime is equal to C1 times the derivative of this cosine. I put this up here as a reminder, but I probably should have put it down here. I'm taking the derivative of this function here. So I have C1 times the derivative of cosine, which is going to be, because it's a negative, derivative of cosine is negative sine, so I'm going to get negative 17.2, the sine of 17.2t. I'll close that, that's a C1, plus C2 times the derivative of this sine expression, and that's going to be 17.2 times the cosine of 17.2t. And if I tidy that up, I get x sub h prime is equal to negative 17.2 C1, the sine of 17.2t, plus 17.2 C2 times the cosine of 17.2t. And now I can plug in the values for the second set of parameters, the second set of conditions here. So let's do that. When t is 0, x prime is 1.5. So I get negative 17.2 C1, the sine of 0, plus 17.2 C2 times the cosine of 0. And this time, because I've taken the derivative, when I had down here, my cosine, my sine was my second term, and that went to 0. My cosine was my first term, that went to 1. Here they're reversed. So I'm going to have my sine term going to 0. This cosine goes to 1. And I'm left with 1.5 equals 17.2 C2. And all I need to do now is divide by 17.2. And I'll get my C2. Although what I'm actually going to do is divide this 1.5 by this nasty number here, because I want to keep it as accurate as possible. So I'll do that on the calculator, and that's going to give me, let's see, can I scooch this over? No, I cannot. So let me do this off camera. All right, so here was my here's my equation. I had my h prime, my x prime, and I plugged in 1.5 for that. I plugged in 0 for t, so I got a 0 here, and I got a 1 here, so I have the 17.2 C2. So that gives me 1.5 equals 17.2 C2. That's this equation right here. Divide both sides by 17.2, but actually I divided by the square root of 294.3. I actually did this arithmetic for accuracy's sake, and I got this answer here. So this is my C2 value. C2 is approximately, but to several places. I think we'll be okay with that. So I have that value now as well. What did I do with my C1? I highlighted it in white, so I'll do the same thing here. So I have those two values now. That means I can go back to this equation and replace C1 and C2 with their values. I think I'm going to do that up here, if I could squeeze it in. I have as my solution x equals, now I don't really need the x sub h anymore. I use that notation here just because I've kind of gotten used to it. But the original equation is a homogeneous equation, so I don't really need this. This is the equation I would need to add a particular solution to if I had a non-homogeneous equation, but I don't. I have a homogeneous equation. So I'm just going to write it as x equals C1, which is negative 0.55, times the cosine, and I'll write it as 17.1552. That's the actual, that's a more accurate value that I got for this square root. In fact, if I change it here, the main reason I changed it in the first place was to save space, not have to write so much. So I didn't want to use too many decimal places. But now that I've done the work, I can actually use more accuracy to write out my final answer. So I have so far x equals C1, this is what my C1 turned out to be, times the cosine of the square root of 294.3 times t, plus C2, which was 0.087437. How many decimal places should we? We'll just go with one more. Times the sine of 17.1552 t. And that is my answer, if you want it in that form. Remember, though, that we can also write this in another form, and that is x equals r times the cosine of omega naught t minus delta. And in order to do that, I'm going to need to figure out what r is. I'm going to need to figure out what omega is and what delta is. Well, omega is pretty easy, because remember that in this form, I have to go back to a previous screen, but in this form, this number right here is the same as this number right here. So if I were to rewrite this as the difference of two angles, the cosine of the difference of two angles, I would end up with the number that I get here would be the same as the number that I have here. So omega is 17.155. 1552. And there's our t minus, and we need to figure out what delta is. And we still need to figure out, there's delta, and we still need to figure out what r is. But also remember that we said in an earlier part of this video that I'm borrowing space all over the place here. R was just equal to the square root of C1 squared plus C2 squared. And I'll just tell you here that that is approximately, because I don't want to take a lot of time or a lot of space, you can do the arithmetic there yourself. That value is about 0.557, so 0.557. How do you find it? Well, you know what C1 and C2 are. You just square these, add them together, and take the square root. Remember that that's the hypotenuse of a right triangle. So we have 0.557 for our R value, 0.557. And then delta was equal to the arctan of C2 over C1. Again, you can do that arithmetic yourself. When I do it here for this problem, I get 2.98400, so we'll just go with 2.984. So I have 2.984. And so another way to write this, let me get my pointer, another way to write this equation is as this equation. They're equivalent. And sometimes you're going to want it in one of these forms, and sometimes you're going to want it in the other form. So there you have it. That is an undamped mass spring system with no external forces. That's what that 0 there tells me. Undamped because there's no first derivative term. And once I figured out what the initial conditions were, which I had to do by pulling the information out of the text, I was able to find K. I was able to find the value K that goes in front of the undifferentiated term, the undifferentiated X. And from there, I replaced the M with 2 from this other situation, and I used the rest of that. I used my previous knowledge to figure out what the solution was. And then here, I changed the answer from one form into another. So there's actually a question on your in your auto-graded homework that is very much like this. In fact, I did this problem from that question because I knew it would cover everything we've talked about so far, and it would give you an opportunity to see how one is done, and then you can practice on your own. The question like this, if there is one on the quiz or on the exam, will be a bit different, but the one on the homework is very much like this. All right, we also need to talk about undamped systems, but I'm going to do that in a separate video.